welcome to everybody tuning in for another deep dive.
Yeah, thanks for having me.
I'm so pumped for this one because we're tackling a question that's been bugging physicists for like almost a century.
Oh, yeah.
Yeah. So get this, can quantum mechanics really describe reality like as we experience it?
I mean, that's a big one.
Right. It's a biggie. And for our guide on this journey, we're going way back to 1935
Yeah, okay.
to a paper by some pretty heavy hitters in physics, Einstein, Podolsky, and Rosen.
I've heard of them.
Even the title of this paper is enough to make your head spin a little bit.
Oh, I bet. What is it?
Ready for this? Can quantum mechanical description of physical reality be considered complete?
Wow. Just like straight to the point, huh? No messing around.
No messing around. But don't worry, we're going to unpack it all together.
All right, sounds good.
Okay, so before we get into all the really complex stuff like wave functions and all that, let's start with like the basics. What were these guys even getting at with this whole physical reality thing?
Okay, well, they started with a pretty simple idea. If you can predict something with certainty without, like, actually messing with it, then there's got to be something real about that thing. Makes sense, right?
Yeah. So it's all about predictability. But isn't quantum mechanics known for being, well, a bit uncertain?
Exactly. And that's where things start to get a little messy. You see, the paper uses this very, like, straightforward definition of reality to point out a potential problem with how quantum mechanics describes the world.
Ooh, this is where it starts getting interesting. So how does quantum mechanics challenge this whole idea of predictability then?
Right, so one of the key players here is something called the wave function.
Okay.
In quantum mechanics, the wave function is basically a mathematical description of a particle's state.
Okay, but what does that actually mean, though?
All right, so think of it this way. Imagine flipping a coin. Before it lands, you know it's got the potential to be heads or tails, right?
Sure, yeah.
The wave function is kind of like that. It gives you the probabilities for all the different outcomes, but it doesn't actually tell you for sure what the outcome will be until you measure it.
So it's all about possibilities, not certainties.
Yeah.
That already feels kind of weird. Like the act of measuring something is actually like influencing reality.
Yeah, and that's exactly the kind of strangeness that this paper is trying to grapple with. And to illustrate this point, they came up with a thought experiment, the famous EPR paradox.
Okay, so I've heard of this, entanglement. How does that work? Is it like some kind of telepathy between particles or something?
It's even weirder than telepathy. Imagine like two gloves from a pair, but they're separated by a huge distance.
Okay.
You know that if one glove is right-handed, the other one has to be left-handed, right?
Yeah.
Entanglement is kind of like that. It's like these two particles are linked. They always have opposite properties no matter how far apart they are.
Wow. Okay, so what happens in the thought experiment?
So they imagine measuring one of these entangled particles. Let's say we measure its position. Because they're entangled, we instantly know the position of the other particle, even if it's like miles away.
Wait, but how is that a paradox? It just sounds like entanglement doing its thing.
Right, but here's the thing. According to quantum mechanics, you can't know both the position and the momentum of a particle with perfect accuracy at the same time. It's like you can choose to know where it is or how fast it's going, but you can't know both.
Right, the Heisenberg uncertainty principle.
Exactly. But in this thought experiment, by measuring the position of one entangled particle, we're instantly determining the position of the other one, even though we haven't measured it directly. But, get this, we could have chosen to measure the momentum of the first particle instead, which would then give us the momentum of the second one instantly.
So you're saying it's like the second particle has a definite position and a momentum, even though quantum mechanics says you can only know one over the other?
That's the paradox. It's like, how is that even possible? Does it mean quantum mechanics is missing something? Or is it telling us that our very idea of what reality is just completely wrong?
Okay, my head is starting to spin a little bit. So are they saying that quantum mechanics is wrong then?
Not necessarily. The EPR paper doesn't actually give us any easy answers. It's more like they're highlighting this potential blind spot in the theory. They're saying, hey, this quantum mechanics thing is amazing, but it might not be the whole picture.
I see. I'm starting to understand why this paper caused such a stir in the physics world.
Oh, yeah.
Like they're throwing a wrench into everything we thought we knew about how the world works. Okay, but this idea of incompleteness, What does that actually mean? Are they suggesting that there's like something missing from the theory?
Well, one possibility is that there are what we call hidden variables. These are like factors that we haven't discovered yet, you know? And maybe these hidden variables could explain how a particle can seemingly have both a definite position and momentum.
So it's like there's more to reality than we can see,
Yeah.
literally.
Right. It's a fascinating possibility. Or maybe, just maybe, quantum mechanics is complete, but we just need to like fundamentally rethink our entire understanding of what reality even is. The paper really forces us to confront these like mind-bending questions.
This is heavy
Yeah.
stuff. Okay, so before we go any further down this rabbit hole, can you kind of sum up what we've learned from this paper so far?
Absolutely. So, first of all, this paper made physicists really think hard about what they meant by physical reality.
Yeah,
Then it highlighted the weirdness of this whole wave function thing and how it's all about probabilities, not certainties.
right?
And then, of course, there's the EPR paradox itself, which really kind of exposed the potential incompleteness of quantum mechanics and all the profound questions it raises about, well, the nature of reality.
Okay, so we've established that Einstein and his buddies thought that there might be something missing in quantum mechanics.
Yeah.
But what happened next? Did other physicists just kind of ignore this, or?
Oh, not at all. This paper sparked decades of research and debate.
Really?
Hmm?
Did anyone try to actually test these ideas?
Oh, they did. And the results were even more mind-blowing. But that's a story for part 2 of this deep dive.
All right, my brain is definitely needing a little break after that, but I'm also way too intrigued to stop now.
Yeah, it's a lot to take in.
So what happened after this EPR paper dropped this, like, bombshell?
Well, let's just say the physics world, it kind of went into a bit of a frenzy. I mean, here you have Einstein, one of the like founders of quantum theory, seemingly turning against it.
Oh, yeah, I bet. So did anyone actually come up with a way to actually test whether or not quantum mechanics was as incomplete as this paper suggested?
That's where things get really, really interesting. This physicist named John Bell, he came up with a brilliant way to do just that.
Okay, tell me more about this Bell guy and his brilliant idea.
So, Bell, he figured out a way to take this very philosophical debate that the EPR paradox started and turn it into an experiment, something we can actually test. He came up with these inequalities, we call them Bell's inequalities, that would hold true if the world worked according to this idea of local realism that Einstein and his buddies favored.
Local realism. I thought we were talking about quantum mechanics here.
We are, we are. But local realism, it's basically this like common sense worldview that the EPR paper was based on. It says that, things have definite properties even when we're not looking at them, and that no influence can travel faster than light.
Got it, got it. So if Bell's inequalities held up in experiments, it would mean that Einstein and the gang were right and that there was something missing from quantum mechanics, right?
Exactly. But if they were violated, then it would be a huge win for quantum mechanics. And it would suggest that, well, maybe our intuitions about reality need a little bit of an overhaul.
Okay, enough with the suspense. What happened when they actually did these experiments?
Well, starting in like the 1970s and 80s, physicists started performing all these increasingly sophisticated tests of Bell's inequalities. And guess what?
Don't tell me. They found evidence for entanglement.
They did. The experiments consistently violated Bell's inequalities. They were confirming what quantum mechanics was predicting.
Wow, so does that mean that Einstein was wrong?
It's not that simple, really. These experiments, they showed us that the universe is even weirder than Einstein could have imagined.
Okay.
They confirm that entanglement is a real thing and that this like spooky action at a distance that he was so skeptical of, it really does happen.
Okay, now my mind is officially blown. Does this mean we need to, like, throw out our entire, like, common sense understanding of reality then?
It might not be that drastic, but it definitely requires us to be a little bit more, flexible in our thinking. These experiments really suggest that, well, the world doesn't quite work the way we intuitively think it does.
Right.
The universe is full of all this interconnectedness and non-locality, and it's really through the lens of quantum mechanics that we're starting to understand these, like, deeper truths.
Okay, so this EPR paradox,
Mm.
it wasn't just some theoretical mind game
Huh.
then. It actually had a real impact on how physics developed.
Oh, absolutely. It forced physicists to really confront some of the most fundamental questions about, like, what is reality and what are the limits of what we can know. It led to the development of all these new experimental techniques. And it really helped to solidify quantum mechanics as one of the most successful theories in, well, all of
So
science.
it's amazing how just one paper can have such a huge ripple effect. But I gotta say, I'm still having trouble, like, really wrapping my head around what it all means. If the world really is as interconnected as these experiments are suggesting, what are the, like, implications of that?
Well, that's a question that physicists and philosophers are still grappling with even today. This whole EPR paradox and the experiments that it inspired, they kind of opened up this, like, Pandora's box of possibilities.
Like what?
Well, for example, some physicists believe that entanglement, that spooky action at a distance, we could actually harness that. We can use it to create all these new technologies like super secure communication systems or maybe even quantum computers that could like revolutionize computing as we know it.
Now, that's what I call mind-blowing. But before we get too carried away with all the futuristic applications, I think we need to take a step back and just try to, like, digest everything we've learned so far.
Yeah, good idea. It's easy to get lost in all the excitement.
Okay, so let's do a little recap here. The EPR paper challenged the completeness of quantum mechanics. But then, experiments, inspired by that very paper, they actually ended up confirming the weirdness of the quantum world, forcing us to really reconsider everything we thought we knew about reality.
You got it. And along the way, we encountered some pretty wild concepts. Entanglement, Bell's inequalities, non-locality.
It's enough to make you question, like, literally everything you thought you knew. So what does this all mean for, the average person out there who's not a physicist?
Hmm.
Why should we care about these, like, mind-bending ideas?
That's a great question. I think like deep down, we all have this innate curiosity about the nature of reality. We want to know like, how does the world work? What is it made of? What is our place in all of this?
You're right. It's like we're all these natural-born explorers trying to figure out the universe around us.
Exactly. And while the implications of quantum mechanics might seem, abstract and kind of far removed from our everyday lives, they have the potential to completely transform our understanding of everything, from the tiniest particles to the vastness of the cosmos.
So even though most of us will never set foot in a physics lab, we can still appreciate the impact that these ideas have on how we see the world.
Absolutely. And who knows, maybe one day we'll all be using quantum computers and communicating through entanglement. The future is full of possibilities.
Speaking of possibilities, didn't you say that there are different interpretations of what all of this means, like different ways of understanding the implications of quantum mechanics?
Right. The EPR paradox didn't just like settle the debate, it actually sparked a whole new set of questions,
Yep.
different interpretations, and that's actually what we'll be diving into in the final part of our deep dive.
Okay, so we've talked about the EPR paradox and Bell's inequalities and all this other mind-bending stuff, but you mentioned that there are different ways of actually, like, interpreting what it all means. Can you unpack that a bit?
Yeah, so it's kind of like, we've climbed this huge mountain of evidence showing us that the world is a lot stranger than we thought. And now we're standing at the peak, looking out at all these different valleys, these different paths we can take down.
Okay, I like that analogy.
Mm.
So what are some of these different paths or, interpretations of quantum mechanics?
Well, one of the most popular interpretations is called the Copenhagen interpretation. It's kind of like the orthodox view, the one that most physicists, learn in textbooks and stuff.
So what does the Copenhagen interpretation actually say then?
Well, it essentially says that, like, we can't really know what's going on in a quantum system before we measure it. It's the act of measurement itself that forces the system to choose a specific outcome.
So it's like until we measure it, the particle is in this fuzzy state of possibilities, like that coin flip we were talking about earlier.
Exactly. And the Copenhagen interpretation says that, we shouldn't even worry about what's really happening before we measure it. It's like the probabilities are all that matters.
That's a pretty pragmatic approach, I guess, but it kind of feels like we're just like sweeping the mystery under the rug.
I get that. And honestly, that's why there are other interpretations out there, ones that try to provide a more like complete picture of what might be going on.
All right, well, give me one of these alternative interpretations then.
Okay, so one that's gotten really popular in recent years is the many worlds interpretation, or MWI. It's a pretty wild one.
Oh, I like wild. Tell me more.
So basically, instead of saying that the wave function collapses when we make a measurement, the MWI says that every single possible outcome actually happens, each one in its own, like, separate universe, a parallel universe.
Hold on. So every time we make a measurement, the universe, it splits into multiple copies.
Yeah, that's the basic idea. Like, imagine one of those choose-your-own-adventure books, where every choice you make, it creates a new branching storyline.
Right.
Well, in the MWI, it's like every single quantum measurement creates a new branch of reality.
Whoa. So there could be Like countless versions of me out there, all making different choices, living different lives.
Yeah, potentially. It's a pretty mind-boggling idea.
No kidding. But hold on. If all of these other universes are totally separate from ours, is there any way to actually, like, test this idea?
That's one of the biggest challenges for the MWI. It's a very elegant, thought-provoking idea, but it's really hard to actually come up with like definitive experiments to test it.
Okay, I get it. So we've got the Copenhagen interpretation, which is all about probabilities and not stressing about what we can't see. And then we've got the many worlds interpretation, which says that like anything that can happen does happen in some parallel universe.
Yeah.
Are there any other like major interpretations we should know about?
There are actually quite a few, but another one worth mentioning is something called Bohmian mechanics.
Okay.
Sometimes it's also called pilot wave theory.
And what's special about that one?
It's a deterministic interpretation of quantum mechanics. So basically, it says that everything is like predetermined from the very beginning. No probabilities, no wave function collapse, just particles following very specific trajectories. They're guided by this like pilot wave.
So it's like a hidden instruction manual for the entire universe.
Kinda, yeah. It's actually a really appealing interpretation for people who are a bit uncomfortable with the inherent randomness of the Copenhagen interpretation.
But wouldn't that mean that like free will is just an illusion then?
Well, that's a debate for another time. But you see, this is what's so fascinating about this EPR paradox. It didn't just expose, like, the strangeness of quantum mechanics. It also opened this door to this whole universe of different interpretations, different philosophical questions.
It's like this paper was a portal to this whole new way of thinking about the world. So where does all this leave us? After all this talk about entangled particles and parallel universes, what are we supposed to make of reality?
Well, I think the most important takeaway here is that our understanding of reality, it's still evolving. We're constantly learning new things, challenging our assumptions, pushing those boundaries of knowledge.
So it's not so much about finding like the right answer. It's more about embracing the mystery of it all and enjoying the journey.
Exactly. The EPR paradox, it reminds us that the universe is full of wonder, and surprises. And there's always more to discover.
I'm definitely walking away from this deep dive with way more questions than answers, but that's not a bad thing. It's just made me realize how much I don't know and how much there is still out there to explore.
That's the beauty of science, isn't it? It's like this never-ending quest for understanding.
Well said. To all of our listeners out there, thank you so much for joining us on this wild ride through the world of quantum mechanics and, well, the nature of reality itself.
We hope you enjoyed it.
And one last thought to leave you with. If the very act of measurement can influence the reality of a quantum system, what does that say about our own role in shaping the world around us?
It's a question that's been bugging philosophers and physicists for centuries. Maybe the answer isn't in some equation, but in the way we choose to observe and interact with the universe.
Deep stuff. Thanks again for joining me on this incredible deep dive. Until next time, keep exploring, keep questioning, and keep diving deep.